my name is Joy, and over the summer I worked on mesh repair at the Shape Lab, which focuses on computer graphics and computational fabrication. So in computer graphics, 3D models in real life can be put on screen through polygonal meshes, which are just little polygons pieced together bit by bit to approximate a 3D shape, or in some cases, a 2D shape. And these polygonal meshes have a variety of implications across many different fields. So for example, in art and design, in film, we have Pixar, and these animated characters are all made from polygonal meshes. In bioinformatics, architecture, computational design, 3D fabrication, all of these models that are printed out or visualized are done so by using meshes. The only problem with this is that oftentimes when meshes are first produced, either by hand or generated by computer, they are imperfect. They are topologically inconsistent in the sense that they come with open areas, self-intersections, overlapping areas, and the problem with this is that existing mesh software is unable to process or refine them. So the point of my project was to be able to identify these topological imperfections and find a way to fix them. So that was how my project broke down into two parts. First, identification, and then repair. For identification, I explored a very interesting concept in topology called winding numbers. Winding numbers, in a nutshell, are basically just how many times a curve rotates around a given point in a plane. So for example, if you have a closed polygon and the point is within that polygon, the winding number of that point with respect to the polygon is 1, because it rotates fully one time around. And if the point is outside of the polygon, the winding number is 0. For open shapes, it becomes a confidence measure. So as the point comes closer to a closed boundary, it gets closer to 1. And as the point transitions across the open boundary to the outside of the shape, it becomes 0. So in application to my project, for the repair phase of the project, what my program does is first take in an input mesh. So if your mesh is in 2D, you would input the vertices and the edges. In 3D, it would be faces, triangular faces, and the vertices. So I would use existing software like TetGen and Triangle to triangulate the 2D meshes, basically turn a surface input into multiple triangles. And in 3D, tetrahedralize the mesh, so turn these volume-based triangles into literally tetrahedra. After that, I would evaluate the winding number at the center of each of these little subsections, these tetrahedra or triangles. And once I had the list, I would determine a threshold for whether that winding number was outside or inside. So as I mentioned earlier, for open shapes, the winding number degenerates smoothly from 1 to 0 across the boundary. At the boundary, for simple polygons and other shapes, the winding number is 0.5. So anything above 0.5 is considered inside, anything below 0.5 is considered outside. Unfortunately, for many meshes that are either low resolution, which means they don't have a lot of polygon comprising the area, and if they are very intricate, this property does not hold, and the threshold of 0.5 fails. So what my project does is it explores another algorithm to make a unique threshold for each mesh. The results were very nice. Based on the unique threshold generated for each mesh, I was able to repair these identified topological imperfections.